Welcome back to the second module of the first week of getting started with competitive programming. So in this video, we will be talking about a problem called Reversort Engineering, and this will be building up on the reverse sort algorithm that we discussed in the previous video. So just in case you haven't watched that, please make sure that you do before starting this video. Now let's get started as usual with the problem statement. Now, in the previous problem, which was reverse sort, we were given a list of numbers as input, and our task was to calculate the cost of reverse sorting that list. Now, in this problem, our task is going to be exactly the opposite, which is to say that we are now given a cost as input, and our task is to produce a list which has that cost. So specifically, we are given two integers n and c as input, and we have to find a list of n distinct integers between 1 and n such that the cost of applying reverse sort to this list is exactly c, or we conclude correctly that there is no such list. So how do you go about tackling something like this? Well, to begin with, notice that the question allows for the possibility that there might be some values of c for which this task is not feasible at all. So maybe that's a good place to start, to try and understand what's a reasonable range of values for c where this task even makes sense. So let's begin by recollecting what reverse sort actually does. Remember that it goes through n-1 iterations, and in each iteration it tries to locate the minimum element and reverses the subarray from the current location all the way up to wherever the minimum element is. Let's recall a couple of minor but important details. The first is that if at any point you are reversing a subarray of length 1, it may not feel like you're doing any reversing at all, but it still has a cost of 1 unit. The other thing to remember is that the total number of iterations is n-1 for lists of length n. So essentially the last step is something you get for free. With that in mind, let's try and come up with a lower bound for the cost c. In other words, if you're reverse sorting some array of length n, is there a minimum cost that you have to pay irrespective of what the array looks like? If you feel like, take a moment here to pause and think about this question. Alright, so you might notice that reverse sort has n-1 iterations, and because of what we just said, the cost of every iteration is at least 1. There are no free lunches in this entire process at all. So the cost of reverse sorting any array of length n is at least n-1. So if the value of c is strictly less than n-1, then it's pretty safe to declare that there is no such list. On the other hand, let's think about if there is a list whose cost is exactly n-1. Again, feel free to take a minute if you need it to think about this. So if you did have a list whose cost was n-1, what would it look like? We already know that there are n-1 iterations, and each of them has a cost of at least 1. So if the total cost had to be exactly n-1, then we couldn't afford to have a cost of greater than 1 in any iteration. In other words, every iteration must have a cost of exactly 1. Well, when does that happen? Notice that that can only happen if at every step the minimum element in that step is already in its correct position. Therefore, the only arrays who have a reverse sorting cost of n-1 are those which are already sorted to begin with. So in fact, it's interesting to know that for this value of c, the solution is in fact unique. Alright, so far we have seen that the cost has to be at least n-1 for us to have a chance of constructing a list with cost c. Now let's try to understand what's happening on the other end of the spectrum, which is to say, can we come up with an upper bound for the cost c? How large can c be for us to have some hope of constructing a list with cost c? This time you want to think about coming up with a scenario where the cost of reversals is as large as it can be in every single iteration. This will lead to some sort of an upper bound. So think about this for a minute and come back when you're ready. So once again, let's recall that there are n-1 iterations, but notice that the length of the array that the algorithm is working with is shrinking in each step. So in the very first step, you're looking at the entire array, and in the worst case, maybe you have to reverse the whole array. In fact, we have seen examples where this actually happens, right? So in the first step, your cost could be as high as n. But in the second step, since the first element has fallen in place, the subarray under consideration starts from the second index and goes all the way till the end. Again, here in the worst case, it's possible that your cost of reversal is n-1, but it's certainly no more than n-1. More generally, in the ith step, the cost of reversal can be as bad as n-I, but no more. And remember that the iterations only go on till the n-1th index. So putting everything together, we know that the cost of reverse sorting is no more than this sum, and if you work it out, it turns out to be n into n plus 1 over 2 minus 1. So this right here is the maximum cost of reverse sorting any array of length n. So once again, like before, if the cost that we have is greater than this bound, then we can immediately conclude that there is no list of length n whose cost is exactly c. But now the more interesting question is the issue of finding a list which actually realizes this upper bound. So for a given n, can you come up with a list of numbers from 1 to n whose cost of getting reverse sorted is exactly the expression that you see here? Feel free to try this out for some small values of n. I will say that this question is slightly harder than the question of coming up with a list whose cost was exactly n-1. So take your time and come back to this video when you're ready. Alright, so as I was suggesting, let's look at some small values of n. The smallest possible value of n that makes sense is 1, and notice that the cost of reverse sorting the only array of length 1 is actually 0, because remember we have n-1 iterations, and here therefore we will have none. The next value of n is 2, and well, there are only two arrays of length 2 over the numbers 1 and 2. So the array 1, 2 is already in its proper order, and the cost of reverse sorting it is just 1, and the array 2, 1 requires a swap in the first step and has a reverse sort cost of 2. Now, this of course is perfectly valid, but notice that we took a brute force approach to coming up with the solution. This is not likely to scale well for larger values of n, so let's try to arrive at the same conclusion but in a slightly more general way. This may be a slightly funny exercise because we are dealing with a really small array, but bear with me and we will also go through this when n is equal to 3, so hopefully things will become clearer as we go along. So let's think in slightly more general terms about the task of coming up with a list whose cost is as high as it can be. What should we aim for in the first step? Well, in the first step, the maximum cost that we can have is n, which happens when you have to reverse the entire array. When would you reverse the entire array? You would do that if the minimum element is at the very end. So we already know that in our array we are forced to place the number 1 at the last position. Now we have to fill up the rest of the array, which is to say that we now turn our attention to the first n-1 slots of the array. Of course, with n being just 2, we only have 1 slot remaining, and it's no surprise what should go in there. But bear with me, let's just continue thinking about a general strategy for filling up these first n-1 slots. So notice that in the row above, we already have an array of length n-1 whose cost is as high as it can be. So it seems like a tempting idea to just copy paste that array in these n-1 slots that we are yet to fill. What is the effect of this? Well, the first thing is that we are no longer left with a valid permutation because we have copy pasted an array that consists of numbers from 1 to n-1, and we also have a 1 at the very end. But as you will see soon, what really matters is not the specific numbers, but their relative order. So to fix this and to turn the current array into a permutation, let's just bump up each of the first n-1 elements by a +1. This brings us to the array 2, 1, which is the solution that we had identified to begin with by just exploring both the possibilities that we had at hand. So let's just make a note of the cost here and move on to the case when n equals 3, where this whole process might be a little more visible. So notice that as before, to begin with, we have to place 1 at the very last position if we want the first step to have the maximum possible cost. After this, to fill in the blanks like before, let's just pull down a copy of the array from the previous row, and noting that we don't have a permutation yet, let's just go ahead and upgrade each of those numbers by 1. Now notice what happens when you run reverse sort on this array that we have. In the first step, as we predicted, the whole array gets reversed, and that has a cost of 3. But after that, notice that we actually have a fully sorted array. So in the second iteration, we won't get the maximum cost that we are looking for. It's just going to be a cost of 1 for a total cost of 4. So that means that we still have some work to do. So what's going wrong here? Although we did copy paste a full cost array from the previous row, notice that that array gets damaged after the first iteration. We have designed our array so that the first iteration reverses the whole list. So as a result, the list that we carefully copied over from the previous step also gets reversed. But the list that we had in the previous step is the list that we want to see at the start of the second iteration after the first reversal. So to ensure that that's what happens, all we need to do is reverse the list in advance so that the first reversal will reverse it back to what we actually wanted to see. Now you can pause the video here and convince yourself that this list that we have here has a cost of 5, which is the maximum cost that you can expect from an array of length 3. Now you can repeat this process quite predictably for larger and larger values of n, and every time you will be able to leverage the list that you built in the previous step to obtain a full cost list in the current step. So let's recap what we have learned so far. We have established some boundaries on the values of C. We said that C has to be at least n minus 1 and at most n into n plus 1 by 2 minus 1. Anything outside of this is already impossible. And for these specific extreme values, we were also able to come up with strategies for building lists whose costs are these exact values. Notice, however, that we are still left with the question of what happens when C lies strictly between these two extremes. Then by just looking at these inequalities, it's not completely obvious if we can always build a list of length n whose cost is exactly C. But let's think about the recursive approach that we just used for building a list of the maximum possible cost. In fact, let's just play with a few scenarios to build up some intuition, and from there, hopefully we'll be able to develop an actual algorithm. So suppose somebody gifts you an array of numbers from 2 to n whose cost is d. Can you use this array to build an array of numbers from 1 to n whose cost is, say, d plus 1? Well, notice that that's easy. You can do that by just adding the element 1 to the head of the array. This way, the first step essentially has cost 1, and the second step encounters the original array, and from there on, the total cost of the algorithm will be d. Now, what if you wanted to build an array of numbers from 1 to n whose total cost was d plus 2 instead? Well, then the natural thing to do seems to be to push the element 1 to the second position so that the first step will have a cost of 2, and then again you're left with the original array that you started with, and from the second iteration onwards you will have a cost of d. This array that you see right here has a total cost of d plus 2. But now what if you wanted to build an array whose total cost was d plus 3? Well, it seems like the natural thing to do again would be to push 1 a little further up. But remember, just like we had this problem before, this particular array will not have a cost of d plus 3 because the first step will cause a reversal which will mess up with the structure of the original array. In particular, after the first step, the array is going to look like 1, x2, x1, x3, and so on. So you've really lost the base array that you started with. So once again, to fix this, we should just swap the elements x1 and x2, and now this array overall will have the desired behavior. Notice that in the first step, the reversal will give us the array 1, x1, x2, and so on, and that's exactly what we were looking for. Now you can probably see where this is headed. If somebody gives you a base array of numbers from 2 to n with a cost of d, then you can make use of this array to build an array of numbers from 1 to n with a cost of, say, d plus 4, d plus 5, and so on. In fact, you can do this for any d plus x for any x in the range 1 to n. Now let's go back to the big picture and try and understand why all this is useful. So to begin with, remember that when you're working with n, here is the valid range of values for c. c has to be at least n minus 1 and at most n times n plus 1 over 2 minus 1. Now let's add to this picture the valid range of values for c relative to n minus 1. That's going to be n minus 2 for the lower bound and n into n minus 1 over 2 minus 1 for the upper bound. So the idea is that you're starting with a cost c that's in the green range, and if you can subtract from it some amount that will take you to the red range, then the recursive algorithm pretty much writes itself. But the question is, can you always subtract something appropriate? Can you always subtract something that's workable? Well, notice that the difference between the two upper bounds is exactly n. What this means for us is that no matter where the original cost lies, as long as it's lying within the valid green range, we will always be able to subtract a quantity x, which is such that it's between 1 and n, so that we get a cost which lies in the red range. And then we can pass this off to the recursion fairy, which will do its thing, and it'll be able to give us an array whose elements are between 1 and n minus 1, and that has cost c minus x. And of course you can just add 1 to each of these elements to get an array of numbers between 2 and n, which have a cost of c minus x to be reverse sorted. As the final step, what you want to do is add the number 1 in the correct place to adjust for the cost of x. So you want to add the number 1 at the xth position from the left, and everything that you have before the number 1 needs to be reversed, so that when the first reversal happens, you recover the array that you obtained from recursion. So by now I think we have everything that we need to know to be able to implement this solution. So let's just do a super quick high-level recap, and then we will switch over to coding. So the first thing we want to do is check the range of c. If c is not within the valid range, then we can immediately conclude that this is an impossible situation, and we say as much. But if c is within the valid range, then we need to figure out how much we need to shave off from c to land in a valid recursive subinstance. And once we do that, we obtain the array from recursion, we adjust its values, we place 1 in the correct place, and we execute one final reversal to get to the array that has the desired cost. So with all this being said, I think it's time to start coding. If you want to do this yourself, by all means, this is your usual spoiler alert. You might want to pause the video here and come back to it after you've given it a shot yourself. Alright, so we have our usual setup here, and as before, I've pulled in the values of the sample inputs and outputs for your reference in the files to the right. Now, the sample outputs for this problem are a bit different from usual in the sense that it's not going to be a character by character match as it usually is for most problems. Notice that for some values of n and c, there might be multiple arrays of numbers between 1 and n whose cost is exactly c. In this case, the problem description says that as long as you print any one of them, your answer will be accepted. So your judge in this case is not going to be doing a character by character comparison with some sample output, but rather it's going to take up the array that you output, and it's going to compute the cost of reverse sorting it and check if it matches the expected cost. So if your output doesn't match with the sample output, maybe because you had a different way of generating these arrays, then don't worry about it too much. Although I would recommend writing down a function that computes the cost of reverse sorting an array. You have probably already done this if you have solved the previous problem. So you could use that function as a way to sanity check your own answers. So once you're producing an array, just use this function to compute its cost and see if it matches with the expected cost, rather than trying to do character by character comparison with the expected output, especially if it doesn't match. Anyway, moving on, I have already set up the the parts about taking in the input, and the output format is the usual CodeJam output format. You have to output case number X followed by either the list or the word impossible, depending on the situation. So let me just get rid of this and come back to the code. What's already done for you is the basic case analysis that we discussed in the beginning. So if the cost C is not in the appropriate range that we discussed, then we just print impossible directly. Otherwise, we have a helper function here which will actually construct this array for us, and you just print this array in the next step. So let's just focus on building out this helper helper function, because then we would pretty much be done. So let me increase the font size before moving on. Right. So the construct function takes 3 parameters as input. The first 2 are quite natural. It's the length of the array you want to construct, that's n, and it's the cost that you want to achieve, that is c. But the third parameter tracks the current minimum value of the array. To begin with, of course, this is 1, but in general, as you unravel the recursion, you will want to increase the value of this minimum element. There are other ways of implementing this, but I just found this one to be the most convenient. So let's try and see how we would actually do this. So let me just begin by pasting the function signature to save time. So n and c are defined as before, and m is the variable that we will use to track the current minimum. Now, whenever I'm writing a recursive function, I like to get the base case out of the way first, just to avoid dangerous situations. So the natural base case here is when n is equal to 1. So this is an array of length 1, where the minimum element has to be m, and we don't have to worry about whether we are working with a valid cost, because we kind of know that to be a precondition. So I'm not going to really check for anything. The cost here must in fact be 0 by the time we have hit the base case. So if you want, you could write a conditional to check for this, but I'm reasonably confident that because the costs were within the valid range to begin with, they will continue to be within the valid range when we come down to the base case. So here I'm just going to return the trivial array with just the element m. All right, the more interesting case is what follows. So let me just pull up the picture which represents our main solution idea. So these are the relevant ranges that we are working with, and I'm just going to get one easy case out of the way, which is to say that when you reduce the cost by just 1, right? If you already fall within the valid range for n-1, then let's just do that and add the number 1 in the beginning, okay? So again, just to save time, I'm going to copy paste this section of the code here, and let's just take a look at what we are doing. So we are saying that if c-1 is at least n-2 and c-1 is at most n into n-1 over 2 minus 1, then, well, let's just invoke this function with length n-1, cost c-1, and of course the minimum upgraded to m+1. So we get this array, and then we just add the current minimum to the start of this array. Okay, in the beginning, of course, this will be 1, but in a generic situation, you want to add the minimum element in the beginning and append the constructed array at the end. Okay, so hopefully this case is clear. Otherwise, we just have a little bit of extra work to do, which is to say that we have to figure out how much to subtract from the cost c before delving into the recursion. So this is the case when the current value is kind of between the right red point here and the right green point here. When you're here, you essentially know that you're within an n length band, but you need to figure out exactly where you fall so that you can subtract the right amount to get into the safe zone with respect to the red range in some sense. So let's write down that difference. It's essentially going to be the current cost minus this lower bound here. That's what you need to subtract, right? So the current cost falls somewhere in this range, and if you subtract n times n-1 over 2 minus 1 from it, then you would have x, which is what you want to subtract. So I'm going to call that difference delta. And now what we want to do is we want to construct an array whose cost is essentially c minus delta, right? And an array of length n-1, and as usual with an upgraded minimum, which is n+1. Okay, so we are going to invoke invoke the current function. This is essentially the recursive step. Now, in the previous case, we could just place m at the head of the array. Now we have, again, a little more work to do, which is to say that we need to find the right place to place the minimum element m, and then we need to reverse everything that comes before it. So let's just go ahead and do that. What we are going to do is, first of all, convert this string into an array, because that's going to be useful for the kind of manipulations that we will need to be doing later, in particular reversing a part of the array and so on. Notice that this array has the minimum element at the first position, because that's all that we have done so far. Now let's just go ahead and see if we can perform the reversal that we need to do. So let's just focus on what's inside the join function. That's the array manipulation that we are doing. So notice that we're working with new array, which just has the minimum element followed by everything we got from recursion, and we are walking up to the deltath element. Remember that delta is excluded because of zero-based indexing, and we essentially need to reverse that entire chunk, and this is the Pythonic notation for doing that. And then we simply add on all the remaining elements of the array. And since construct needs to be returning a string, all we are doing here is converting this array back to a string, and at this point we are actually done. Now there are some small formalities that remain, so let's take care of them first. So notice that we haven't yet returned the answer that we have so painstakingly created, so let's do that. I mean, one thing that's nice about VS Code is that it gives you this muted color for those variables that you have declared but you haven't used yet. So that's already a hint that I've left something hanging. So let's return the answer, and I think at this point all that remains to be done is to actually run this code and see how it works. So let me add the template to redirect the input output to files, and let's run this program. So we get some output. Notice that if I were to run a diff on my output with the expected output, then we do get some differences here. You can visibly see that the arrays that we are producing are a little bit different from the official outputs. As I said in the beginning, this is nothing to worry about, but I will leave it as a bit of an exercise for you to either come up with a different way of generating these arrays that possibly match with the sample outputs, although it's not clear to me if the sample outputs were driven by an algorithm that generated them, or if they just wanted to deliberately throw us off by using solutions that are different from perhaps the natural algorithm. But in any case, what is really worth doing is sanity checking that the arrays you're generating do have the cost that you expect them to have. So for instance, for the first array here, we were supposed to have a cost of 6. So let's quickly see what Reversort would do here. In the first step, you would have a cost of 1 because the minimum element is sitting right there. The next step, you would have a cost of 3 because the minimum element is at the very end. At this point, your array would look like 1, 2, 4, 3. So the last two elements would need to be swapped in the last step. So that's an additional cost of 2. So this array does have a total cost of 6, and you can also verify that the array that appears in case number 3 has a cost of 12. Again, do try this out. Try writing a version of the solution on your own, and do upload it on the CodeJam platform and let us know how it went for you. I look forward to seeing you in the next video. That'll be all for now. Thanks so much and have a great time.